The universe is a grand performance, but the real actors are invisible. Everything you see, from a single star to an entire galaxy, is moved by hidden forces operating in the shadows of reality. These unseen influences, from the cosmic scale to the quantum realm, dictate the birth of stars, the fate of galaxies, and the very fabric of existence itself. By the end of this journey, you will understand the 30 most mysterious and powerful hidden hands shaping everything we know. What cosmic pressure is tearing space itself apart at an ever-increasing rate? How can particles billions of light years apart communicate instantly? These are not just questions, they are the invisible rules of the game. So, what is the one unseen force you believe must be out there, waiting to be discovered? The greatest discovery in modern cosmology was not finding something new, but realizing we had no idea what most of the universe is made of. The story begins in the late 1990s, when two separate teams of astronomers pointed their telescopes at a specific kind of stellar explosion, a Type 1, a supernova. These explosions are crucial because they are standard candles, meaning they always shine with a known intrinsic brightness. By measuring how dim they appear from Earth, astronomers can calculate their distance with incredible precision. What both teams expected to find was a universe slowing down in its expansion, its galaxies coasting apart under the fading momentum of the Big Bang, gradually pulled back by the collective gravity of all matter. What they found instead was a shock. The most distant supernovae were fainter than they should have been. This meant they were farther away than the standard models predicted. The universe was not slowing down, it was speeding up. Some unseen repulsive force, something woven into the very fabric of space, was pushing galaxies apart at an ever-increasing rate. This force was named dark energy. Today, we know it is not a minor player. It is the dominant component of our cosmos, making up roughly 68% of all the energy in the universe. Think of that for a moment. Everything you have ever seen, touched, or loved, every star, planet, and galaxy, accounts for less than 5% of reality. Dark energy is the silent, overwhelming majority, an anti-gravity acting on the grandest stage imaginable. The leading explanation for this bizarre force is something Albert Einstein proposed, then famously discarded as his greatest blunder, the cosmological constant. In his equations for general relativity, Einstein added a tiny term represented by the Greek letter lambda to keep the universe static, as everyone at the time believed it was. When Edwin Hubble later proved the universe was expanding, Einstein removed it. Now it is back with a vengeance. This constant represents a property of empty space itself, a vacuum energy. Imagine space not as a passive stage, but as an active, seething field. Even in a perfect vacuum at the quantum level, particles and their antiparticles are constantly flickering into and out of existence. This quantum foam generates a background energy that, according to this idea, has a repulsive gravitational effect. It is as if empty space itself has a kind of tension, a springiness that causes more space to generate between any 2 points over time. Picture a grid of galaxies drawn on a rubber sheet. Now imagine the sheet itself is not just stretching, but new rubber is constantly being created between every point on the grid. The galaxies are not moving through space away from each other, they are being carried apart by the relentless generation of new space itself. That is the repulsive push of dark energy. Yet, this elegant idea comes with a colossal puzzle. When physicists try to calculate the expected strength of this vacuum energy from quantum theory, the number they get is wrong. Not just a little wrong, but 120 orders of magnitude wrong. It is the worst theoretical prediction in the history of science. This means our understanding of the quantum world and our understanding of gravity on cosmic scales are fundamentally, catastrophically incompatible. Dark energy is not just a mystery, it is a screaming clue that our most fundamental theories of reality are incomplete. What other rules might we be missing when the force that controls the destiny of everything remains almost entirely unknown? If dark energy is the mysterious force pushing the universe apart, then dark matter is the ghostly glue holding it all together. This is the second unseen architect of our reality, an invisible substance that provides the gravitational skeleton for every galaxy we see. The story of its discovery begins not in deep space, but in the careful observations of a single galaxy's spin. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a vast collection of galaxies. He measured how fast individual galaxies were orbiting the cluster's center and made a startling calculation. The visible mass of all the stars and gas was nowhere near enough to generate the gravity needed to keep the cluster from flying apart. He proposed the existence of what he called dunkel materie, or dark matter, to account for the missing gravity. But the most compelling evidence came decades later from Vera Rubin and Kent Ford. They meticulously mapped the rotation of the Andromeda galaxy, expecting to see stars on the outer edges moving slower than those near the bright center, just as planets farther from the Sun orbit more slowly. What they found defied all expectations. Stars at the galaxy's outer rim were orbiting just as fast as those near the core. According to the laws of gravity, this should be impossible unless the galaxy was embedded in a massive, invisible halo of matter, a halo extending far beyond the visible edge of the stars. This halo is dark matter. We cannot see it because it does not emit, absorb, or reflect any form of light or electromagnetic radiation. It is utterly transparent. Yet its gravitational influence is undeniable. We see its fingerprints everywhere. When we look at massive galaxy clusters, we often see distant galaxies behind them appear stretched and warped into strange arcs, like light passing through a giant cosmic lens. This effect, called gravitational lensing, reveals that the cluster's total mass, which bends the light, is far greater than the sum of its visible parts. The most precise map of dark matter comes from the faint afterglow of the Big Bang itself, the cosmic microwave background. The tiny temperature fluctuations in this ancient light are a blueprint of the early universe, and they tell us that dark matter makes up about 27% of the cosmos. Combined with dark energy, this means over 95% of the universe is completely invisible to our telescopes. So what is it made of? The leading idea is that it consists of a sea of exotic, cold dark matter particles. Cold means they move relatively slowly, allowing them to clump together under gravity to form the vast halos that cradle galaxies. These hypothetical particles, with names like WIMP or weakly interacting massive particles, would barely interact with normal matter except through gravity. They would pass through you, through the Earth, and through entire stars as if they were not even there. Picture a bustling city at night, seen from a high vantage point. The city's shape is defined by the streetlights and illuminated buildings, the visible matter. But the true structure of the city, its roads, its foundations, its underlying grid, remains unseen in the darkness. That hidden grid is dark matter. It is the invisible framework upon which the luminous universe is built, dictating where galaxies form and how they evolve. Without this ghostly scaffolding, galaxies like our Milky Way would have never coalesced, and stars like our Sun would have never been born. We are here because of something we cannot see. So we must ask, if this mysterious substance is everywhere, flowing through us at every moment, what other invisible currents might be shaping the story of our existence? Empty space is not empty at all. It is a turbulent sea of energy, a quantum foam where the rules of reality as we know them break down. This is the domain of quantum vacuum fluctuations, the third unseen force shaping our universe. To understand it, we must shrink our perspective from the vast cosmic web to the unimaginably small. At this scale, Werner Heisenberg's uncertainty principle reigns supreme. This fundamental law of quantum mechanics states that we cannot simultaneously know certain pairs of properties, like a particle's exact position and its exact momentum, with perfect precision. There is always a fuzziness, a fundamental uncertainty baked into the fabric of reality. But this principle has a profound consequence for energy. It means that even in a perfect vacuum at the absolute zero of temperature, space cannot be completely still. For incredibly brief moments, the universe allows for a loan of energy as long as it is paid back almost instantly. This loan manifests as pairs of virtual particles, a particle and its antiparticle, spontaneously flickering into existence and then annihilating each other in a flash. This is not a metaphor. We can observe its effects. In the 1940s, a Dutch physicist named Hendrik Casimir predicted a strange phenomenon. If you take two perfectly smooth, uncharged metal plates and place them incredibly close together in a vacuum, they will be gently pushed together. Why? Because the seething quantum foam of virtual particles exists in all possible wavelengths. But in the narrow gap between the plates, only certain wavelengths can fit. This means the pressure of virtual particles pushing from the outside of the plates is slightly greater than the pressure from the inside. The plates are literally squeezed together by the restless energy of nothingness. This Casimir effect has been experimentally confirmed, proving that the vacuum of space is alive with transient activity. Now consider the scale of this phenomenon. These quantum fluctuations are happening everywhere, at every point in the universe, all the time. Each event is vanishingly small, but when you add up the infinite energy of this sea of virtual particles across the entire cosmos, you get a staggering number. This is where we circle back to the greatest mystery of dark energy. This vacuum energy, this cosmological constant, should be the most natural candidate for the force accelerating the universe's expansion. It is a repulsive pressure inherent to space itself. Yet, as we saw, the calculated strength of this quantum vacuum energy is catastrophically larger than the observed strength of dark energy. It is off by a factor of 1 followed by 120 zeros. This is not a small error. It is the clearest signal that something profound is missing from our understanding. Perhaps the virtual particles cancel out in ways we do not yet comprehend. Or maybe dark energy is something else entirely, a new field or a modification of gravity itself. But the quantum vacuum remains. It is the backdrop against which all particles dance, the simmering pot from which matter itself may have emerged in the first moments of the Big Bang. This invisible churn at the smallest scales may well hold the key to the fate of the largest structures in the cosmos. If the void itself is this restless, what other secrets is it hiding in plain sight? The quantum foam is a seething chaos, but another invisible field brings order to the particle zoo. This is the Higgs field, the cosmic molasses that gives particles their mass. Without it, the universe would be a blur of light-speed chaos with no atoms, no stars, and no us. Think of the Higgs field not as a substance, but as a uniform, invisible energy that fills every cubic inch of the cosmos like a vast, still ocean. Different fundamental particles interact with this field in different ways. Photons, the particles of light, do not interact with it at all. They zip through unimpeded, which is why they have no mass and travel at the universe's ultimate speed limit. But other particles, like quarks and electrons, do interact. Imagine wading through a deep pool of water. The water resists your motion, making it harder to start moving and harder to stop. That resistance is inertia, and that is mass. A particle moving through the Higgs field experiences a similar drag. The more strongly a particle interacts with the field, the more mass it acquires. The top quark interacts very strongly, so it is incredibly heavy. The electron interacts only weakly, so it is much lighter. This interaction is mediated by a corresponding particle, the famous Higgs boson. Finding this particle was the mission of the Large Hadron Collider, the most powerful particle accelerator ever built. For decades, physicists predicted its existence, but the Higgs boson is unstable and decays in a fraction of a second. To create one, scientists had to smash protons together at velocities incredibly close to the speed of light, recreating for a fleeting instant the energetic conditions of the early universe. In July 2012, after years of data collection, two independent teams at the LHC announced they had found it. They had detected the telltale decay patterns of a new particle with precisely the right properties. It was the Higgs boson, the quantum fingerprint of the field itself. This discovery was monumental. It confirmed the final piece of the standard model of particle physics, the rulebook for the subatomic world. It proved that mass is not an intrinsic property, but a gift from an invisible field that permeates all of reality. You can picture the universe just after the Big Bang, unimaginably hot and energetic. In that primordial fire, the Higgs field was zero, like a calm sea. As the universe expanded and cooled, this field switched on everywhere at once, like a sudden universal freeze. Particles that were once massless, racing freely at light speed, suddenly found themselves slogging through this new cosmic treacle, slowing down, clustering together, and forming the first stable structures. The Higgs field is the silent sculptor of matter. It is the reason anything has substance. Yet, even this triumphant discovery opens new mysteries. Why do particles have the specific masses they do? The Higgs mechanism explains how they get mass, but not the values themselves. The numbers seem arbitrary, a fine-tuning that allowed for the existence of atoms and life. Was this pure chance, or is there a deeper structure we have yet to uncover? If an invisible field gives everything its weight, what other hidden fields might be waiting, quietly shaping other fundamental properties of our reality? The Higgs field gave particles their substance, but another invisible force had already set the stage for everything to come. In the first sliver of a second after the Big Bang, the universe underwent a transformation so violent and rapid it defies all intuition. This is cosmic inflation, a period of exponential expansion that blew a subatomic speck of space into a macroscopic cosmos, all in less than a blink of an eye. To grasp its scale, think of a single proton, one of the tiny particles in an atom's nucleus. Now, imagine that proton expanding to become larger than our entire observable universe, and doing so in a time span so short it makes a nanosecond feel like an eternity. That is the staggering speed of inflation. It was not an explosion of matter into space, but a hyper-stretching of space itself, driven by a hypothetical energy field called the inflaton. As this field descended from a high-energy state, like a ball rolling down a hill, it released immense energy that caused space to expand at a rate far exceeding the speed of light. This solves two of cosmology's greatest puzzles. The first is the horizon problem. Look at the cosmic microwave background, the ancient light from the infant universe. No matter which direction we look, this afterglow has almost exactly the same temperature. But in the standard Big Bang model, these distant regions could never have been in contact to equalize their temperature, as there had not been enough time for light or heat to travel between them. Inflation fixes this by proposing that every part of our observable universe was once crammed into a tiny, connected region that was then stretched to cosmic proportions, preserving that uniform temperature like a pattern on a balloon being inflated. The second puzzle is the flatness problem. Measurements show the geometry of our universe is remarkably flat, meaning parallel lines stay parallel, and the laws of Euclidean geometry hold true on the largest scales. For the universe to be this flat today, its initial conditions had to be fine-tuned to an unimaginable degree of precision. Inflation acts like a cosmic iron, stretching any initial curvature so dramatically that the universe appears flat to us, just as inflating a balloon makes its surface appear flatter from any single point on it. But inflation's most profound gift was imperfection. As the inflaton field decayed, quantum fluctuations were frozen into the fabric of spacetime. These tiny ripples in density became the seeds for all future structure. Every galaxy, every star, every planet you see is the grown-up version of a microscopic quantum jitter, magnified to cosmic scale by inflation's incredible stretch. We are the children of quantum noise. The search for direct proof of inflation continues, and the most promising clue lies in primordial gravitational waves. These would be ripples in spacetime itself, generated by the violent tremors of the inflatoned field's decay. If detected, their signature would be imprinted as a specific pattern called B modes in the polarization of the cosmic microwave background. Finding them would be like hearing the faint echo of the universe's first cry. While hints have been tantalizing, a definitive detection remains elusive. The inflatoned field has vanished, its job complete, leaving behind an expanded, smoothed, and seeded universe as its only monument. It was the ultimate cosmic catalyst, the invisible hand that prepared the canvas upon which dark matter, dark energy, and all the forces of nature would later paint the grand tapestry of galaxies. If such a transformative power can vanish without a trace, what other fleeting, epoch-defining forces have shaped the cosmos in ways we have yet to dream of? Inflation stretched the universe smooth, but left behind a deeper strangeness woven into the quantum fabric of reality itself. This is quantum entanglement, a connection so intimate and instantaneous it defies our most basic notions of space and time. Albert Einstein famously dismissed it as spooky action at a distance, a phrase that captures both its eeriness and his deep discomfort. The phenomenon is simple to describe, yet profoundly difficult to accept. Imagine you create a pair of particles, perhaps two photons, in a single quantum event. These particles become entangled, their properties linked in a shared, fuzzy quantum state. You could then send one particle to a lab on Earth and its partner to a detector near a star 1,000 light-years away. According to quantum mechanics, neither particle has a definite property like spin or polarization until it is measured. The moment a scientist on Earth measures their particle and finds, say, an upspin, the fate of its distant partner is sealed instantaneously. It will be found to have a perfectly correlated downspin, no matter the vast distance separating them. This is not a signal traveling at the speed of light. The correlation is immediate. It is as if the two particles are not separate entities at all, but two faces of a single coin that only decides if it is heads or tails the moment you look at one side. This has been confirmed through rigorous experiments, closing loopholes that skeptics proposed. Entanglement is real. The implications shake the foundation of physics. It suggests that information, or at least correlation, can exist in a way that transcends space. Some interpretations propose that at a fundamental level, the universe is not local, meaning things here can be directly influenced by things far away without any intermediary. Others suggest that the particles are not communicating, but that our idea of separate particles is an illusion, and they remain part of a deeper, unified whole. This bizarre property is not just a philosophical curiosity, it is the engine of a technological revolution. Quantum computers leverage entanglement to perform calculations in parallel universes of possibility. While a classical computer bit is either a 0 or a 1, a quantum bit or qubit can be both at the same time, a superposition. Entangle many qubits, and their superpositions become intertwined, allowing a quantum computer to explore a vast landscape of solutions simultaneously. It could one day crack codes that would take conventional computers the age of the universe to solve, or simulate complex molecules to discover new medicines. But the greatest mystery entanglement poses is for spacetime itself. If two particles can share information instantly across the cosmos, what does that say about the nature of the distance between them? Some physicists like Juan Maldacena and Leonard Susskind have proposed a radical idea that entanglement might be the very glue that stitches spacetime together. They suggest that the geometric connection we perceive as empty space could emerge from a vast, invisible web of quantum entanglement between the underlying bits of information in the universe. In this view, the spooky link is not a bug in reality, it is the feature that builds reality. So we are left with a breathtaking possibility. The invisible threads connecting entangled particles, threads that ignore the vast gulfs of space, might be the hidden scaffolding upon which space itself is constructed. If that is true, then the greatest distances in the cosmos are, in a sense, an illusion. What other fundamental illusions might our senses be hiding from us? Gravity is not a uniform pull, but a force with a gradient, a difference in strength from one point to another. This subtle variation, the tidal force, is a hidden sculptor with consequences both beautiful and terrifying. It is the reason our moon always shows us the same face and why distant moons can be worlds of fire. The principle is simple, yet its effects are profound. An object in a gravitational field feels a stronger pull on the side closest to the source and a weaker pull on the side farthest away. This difference stretches the object. You experience a microscopic version of this every day. The moon's gravity pulls more strongly on the side of Earth facing it, causing the oceans to bulge outward. The solid Earth also feels this stretch, flexing by several centimeters, but for smaller, weaker bodies, tidal forces become the dominant architect of their existence. Our moon is tidally locked to Earth. Billions of years ago, it likely spun faster, but Earth's gravity created a persistent tidal bulge on the lunar surface. This bulge, slightly ahead of the point directly facing Earth, acted like a handle. Earth's gravity tugged on this handle, applying a constant brake until the moon's rotation slowed to match its orbital period. Now it takes the same amount of time to spin once on its axis as it does to orbit our planet, so we only ever see one hemisphere. This same process is locking many exoplanets to their stars, creating permanent daysides of scorching heat and permanent nightsides of frozen darkness. But tidal forces can also generate immense heat through friction. Look at Jupiter's moon Io, the most volcanically active world in our solar system. Io is caught in a gravitational tug of war between massive Jupiter and the other large moons, Europa and Ganymede. This forces Io into a slightly elliptical orbit. As its distance from Jupiter changes, the tidal forces flex and knead its interior like clay, generating tremendous friction. This friction melts Io's rock from the inside out, driving hundreds of active volcanoes that constantly resurface the moon in lakes of molten sulfur. Where tidal forces become extreme, they transition from sculptors to destroyers. Every massive object has a boundary called the Roche limit. Inside this limit, the tidal force pulling an object apart becomes stronger than its own gravity holding it together. A comet or moon that wanders too close to a planet will be torn into a stream of debris, which can then form spectacular rings like those of Saturn. But the ultimate expression of tidal destruction awaits near a black hole. An object falling toward a black hole experiences such an intense gravitational gradient that the difference in pull between its head and its feet becomes astronomical. The object is stretched into a long, thin strand of matter in a process physicists call, with grim accuracy, spaghettification. Long before it crosses the event horizon, it is shredded into a stream of elementary particles. From the gentle lock that gives us our familiar moon, to the infernal heating of alien volcanoes, to the cosmic shredders at the hearts of galaxies, tidal forces remind us that gravity is not just an anchor, but a relentless and differential pull that shapes, heats, and ultimately dismantles the cosmos. If such a common force can hold such transformative and violent power, what other subtle gradients are at work, quietly bending the universe to their will? Magnetic fields are the universe's great puppeteers, orchestrating the dance of charged particles across the void. These invisible lines of force, undetectable to our eyes, are etched into the fabric of space by moving electric charges, creating a cosmic lattice that channels, accelerates, and contains the fourth state of matter, plasma. Nowhere is their power more vividly displayed than on our own sun. Its churning interior acts as a colossal dynamo, where the motion of superheated plasma generates a complex, tangled magnetic field. This field can become stressed and twisted, erupting through the solar surface as dark sunspots, and then releasing cataclysmic bursts of energy in solar flares and coronal mass ejections. These eruptions hurl billions of tons of charged particles into space at millions of miles per hour, a solar wind that carries the sun's magnetic influence to the very edges of the solar system. When this wind reaches Earth, it does not encounter empty space. Our planet's molten iron core is also a spinning dynamo, generating a protective magnetic bubble called the magnetosphere. This invisible shield deflects the majority of the solar wind, channeling charged particles toward the poles where they ignite the shimmering auroras. Without this magnetic cocoon, our atmosphere would be slowly stripped away by the relentless stellar gale, leaving a barren rock like Mars, whose internal dynamo died eons ago. But the influence of magnetism extends far beyond our solar neighborhood. Our entire Milky Way galaxy is threaded with a vast, diffuse magnetic field. Though incredibly weak, 1,000,000 times fainter than Earth's field, its scale is incomprehensible. This galactic field acts as a guide wire for cosmic rays, the ultra-high-energy protons and atomic nuclei that streak across the universe. These rays are not rays at all, but charged particles, and as such they are bent and redirected by magnetic fields, making it nearly impossible to trace their origin back to a specific source like a distant supernova or active galaxy. The field itself is thought to be generated and sustained by the dynamo effect on a galactic scale, amplified by the motion of interstellar gas and the rotation of the galaxy itself. The dynamo is the universal engine behind these forces. It requires three ingredients: a rotating body, a convecting fluid that can conduct electricity, and an initial seed magnetic field. In a planet like Earth, the rotation spins the molten iron outer core, while heat from the inner core drives convection, stirring the metal. This motion, across the weak initial field, generates electrical currents, which in turn amplify the magnetic field in a self-sustaining loop. A similar process churns within stars, including our Sun. This invisible architecture shapes everything from the weather in space that can knock out satellites to the very paths of the most energetic particles in creation. Magnetic fields are the silent cartographers of the charged cosmos, drawing unseen maps that every electron and proton is forced to follow. If these hidden lines guide the storms of stars and the rain of cosmic rays, what other invisible geometries are directing the flow of the universe? Einstein's spacetime is not a static stage, but a dynamic fabric that can ripple and shake. These ripples are gravitational waves, the ninth unseen force, and their detection has given us an entirely new sense with which to perceive the cosmos. For a century, they were purely theoretical, a consequence of his general theory of relativity. Einstein reasoned that any accelerating mass should generate waves in the fabric of spacetime itself, propagating outward at the speed of light. But the effect is unimaginably tiny. The collision of two black holes, events of almost incomprehensible power, would stretch and squeeze the space between objects on Earth by less than the width of a single proton. Detecting such a minuscule whisper seemed impossible. That changed on September 14, 2015, when the twin detectors of the Laser Interferometer Gravitational Wave Observatory (LIGO) heard a distinct chirp. The signal matched the precise waveform predicted for the final moments of two massive black holes, each about 30 times the mass of our Sun, spiraling into each other and merging. In that cataclysm, an amount of energy equivalent to 3 solar masses was converted, in a fraction of a second, into pure ripples of gravity. we had heard the universe ring like a bell. Since then, LIGO and its European counterpart, Virgo, have listened to dozens of such cosmic crashes. The sources are the most violent events in existence, the mergers of black holes and neutron stars. When two neutron stars, the ultra-dense corpses of dead stars, spiral together, they do not just send out gravitational waves, they also produce a spectacular firework display of light, gamma rays, and heavy elements like gold and platinum, which we can now observe with traditional telescopes. This multi-messenger astronomy, combining gravity's song with light's picture, is like seeing a silent movie for the first time with sound. But gravitational waves offer something even more profound, a direct window into the dark universe. Light can be blocked, absorbed, or scattered by dust and gas. Gravity cannot. Gravitational waves pass through everything unimpeded, carrying clean information from the heart of the most obscured events. They allow us to sense black holes directly, even when they are floating in utter darkness, far from any star to illuminate them. They let us probe the extreme warping of spacetime near an event horizon and test whether Einstein's equations hold true in such brutal environments. The detectors themselves are marvels of precision. Each LIGO facility consists of two 4-kilometer-long arms arranged in an L shape. A laser beam is split and sent down each arm, bouncing off mirrors to recombine. In calm spacetime, the light waves cancel each other out. But when a gravitational wave passes, it minutely stretches one arm while squeezing the other, changing the distance the light travels by a vanishingly small amount. This causes the recombined light waves to flicker, creating the signal. It is like trying to measure a change in the distance to the nearest star that is less than the thickness of a human hair. With this new sense, we are no longer just stargazers. We are listeners to the symphony of space-time, hearing the collisions that shape the galactic landscape and the faint echoes from the universe's earliest moments. If these whispers can reveal black holes dancing in the dark, what other silent conversations of the cosmos are we only now learning to hear? The violent symphonies of colliding black holes are written in gravity, but the quiet chemistry of the stars is governed by a far more subtle hand. Deep within every shining sun, an unseen force is tirelessly rewriting the identities of the universe's most basic building blocks. This is the weak nuclear force, the shyest and most mysterious of nature's four fundamental interactions. While gravity shapes galaxies and electromagnetism binds atoms, the weak force specializes in transformation. It is the master of change, the force that allows one type of particle to literally become another. Its most famous and vital act is beta decay. Picture a lone neutron sitting in an atomic nucleus. Left to itself, it is unstable. Through the weak force, that neutron can spontaneously transform. In a process that takes about 15 minutes on average, the neutron decays into a proton, while also spitting out an electron and an almost ghostly particle called an antineutrino. The nucleus has now changed. It has gained a positive charge. This simple swap is universe-altering. It is the primary way stars like our Sun generate their energy. In the stellar core, under immense heat and pressure, protons' hydrogen nuclei are forced together. But two positively charged protons repel each other fiercely due to electromagnetism. The weak force provides a miraculous loophole. It allows one of those protons to turn into a neutron. This transformation creates a bound state, a deuterium nucleus, opening the door to the chain of nuclear fusion that builds helium and floods the cosmos with light. Without this subtle, identity-shifting force, stars would never ignite. The weak force's power comes from its unique messengers, the W and Z bosons. These are the heavyweights of the force-carrying particles, immensely massive compared to the weightless photon of electromagnetism. And that mass is the key to the force's personality. It makes the weak force incredibly short-ranged, effective only over a distance smaller than a single proton. This is why it operates deep within the heart of atoms and stars, a hidden foreman in the subatomic workshop, but its role does not end in stellar nurseries. When a massive star reaches the end of its life and explodes as a supernova, the weak force takes center stage in the most dramatic act of cosmic alchemy. In the unimaginable fury of that explosion, a blizzard of neutrinos and antineutrinos floods out from the collapsing core. These ghostly particles, which only interact via the weak force and gravity, carry away a tremendous amount of energy. But crucially, they also facilitate reactions that rapidly transform protons and neutrons. This neutrino-driven wind, mediated by the weak force, is the cosmic forge where elements heavier than iron are hammered into existence. The gold in your jewelry, the uranium in the earth, the iodine in your body, all were born in the seconds following a supernova, crafted by the subtle, transformative touch of the weak nuclear force. It is a force that works in shadows and whispers, operating at scales we can scarcely conceive, yet it is the indispensable author of atomic diversity and the very reason stars shine. If such a hidden, short-range interaction can seed the universe with the elements of life, what other miniature, transformative engines might be ticking away in the dark? While the weak force specializes in transformation, another fundamental power operates with sheer, unyielding strength. The strong nuclear force is the mightiest glue in the universe, the invisible bind that holds reality together at its most fundamental level. Its domain is the heart of the atom, where it performs two monumental tasks. First, it binds quarks together to form protons and neutrons. Second, and just as crucially, it overpowers the fierce electromagnetic repulsion between positively charged protons to hold the atomic nucleus together. Without this force, every atom in existence would instantly fly apart, and the cosmos would be nothing but a diffuse haze of disconnected particles. The carrier of this incredible force is the gluon. Unlike the photon of electromagnetism, which is massless and does not carry charge itself, gluons are unique. They carry the very charge they are meant to mediate, a property known as color charge. Do not let the name fool you. It has nothing to do with visible color. It is simply a whimsical label for a type of charge that comes in three varieties, which physicists call red, green, and blue. Quarks carry one of these color charges, and the rule is that all composite particles, like protons and neutrons, must be color neutral or white. This is achieved by combining three quarks with one of each color, or a quark and an antiquark with complementary colors. Gluons constantly exchange between quarks, carry a mix of a color and an anticolor, acting like sticky strands of pure force that keep the quarks perpetually bound. This leads to one of the most bizarre properties in all of physics, asymptotic freedom. The strong force behaves in the exact opposite way of gravity or electromagnetism. The closer two quarks get, the weaker the strong force between them becomes. It is as if the glue loosens its grip, but try to pull two quarks apart, and the force becomes unimaginably strong, increasing with distance. It is like stretching a rubber band. The farther you pull, the harder it resists. So hard, in fact, that the energy you put into separating them is enough to create new quark-antiquark pairs from the vacuum, resulting in new bound particles rather than free quarks. This is why we never find an isolated quark. They are forever confined within protons and neutrons by this unbreakable elastic prison. This mighty binding is what makes nuclear fusion possible. In the core of a star, hydrogen nuclei protons are squeezed together by gravity. Their positive charges repel each other with tremendous electromagnetic force. But if they can be pushed close enough to within a femtometer, a millionth of a billionth of a meter, the strong nuclear force takes over. Its short-range but overwhelming power fuses the protons into a helium nucleus, releasing the binding energy as sunlight. Every photon that warms your skin began with this subatomic handshake. The strong force's ultimate test comes in a supernova. When a massive star's iron core collapses, protons and electrons are crushed together under such pressure that they merge via the weak force to form neutrons. What is left is a seething ball of nearly pure neutrons, held against their own immense density solely by the strong force. If the remaining core is between about 1.4 and 3 solar masses, the strong force wins, creating a stable neutron star, an object so dense a single teaspoon would weigh as much as a mountain. But if the core is heavier, even the mighty strong force is overwhelmed by gravity, and the collapse continues into a black hole. From the stability of the atoms in your body to the fury of a stellar explosion, the strong nuclear force is the ultimate cosmic welder. It forges the elements and defines the limits of matter itself. If this force, operating in a space smaller than a proton, dictates the fate of stars, what other microscopic rules are secretly governing the grandest structures of all? The strong force welds nuclei together, but the true architect of our tangible world is a force you feel with every touch. Electromagnetism is the master builder of reality, the invisible sculptor of light, matter, and life itself. While gravity reigns over the cosmic stage and the nuclear forces work in hidden chambers, electromagnetism is the force that paints the world in color, forges the bonds between atoms, and writes the very code of chemistry. It operates through the exchange of massless photons, particles of light, which gives it an infinite range. From the atomic scale to the edges of the observable universe, its influence never fades. Its most fundamental act is to bind electrons to atomic nuclei. The negatively charged electron is held in orbit by its attraction to the positively charged protons, creating stable atoms. Without this electromagnetic glue, atoms would simply evaporate into a formless cloud of particles. But its genius lies in the leftovers. When atoms come together, the complex dance of their electron clouds creates chemical bonds. Whether it is the strong covalent bond sharing electrons to create a water molecule, or the weaker ionic bond that gives salt its crystal structure, every link in every molecule of your body, every strand of DNA, and every compound on Earth is a masterpiece of electromagnetic negotiation. This force does not just build, it communicates. Every photon of light is a ripple in the electromagnetic field. The warmth of sunlight on your skin, the colors of a rainbow, the signal from a distant radio tower, and the X-rays that reveal a broken bone are all manifestations of this single, versatile force. It fills the cosmos with radiation across the entire spectrum, from the long, cold waves of radio to the blistering fury of gamma rays. This electromagnetic symphony is how we perceive almost everything about the universe beyond our own planet. Yet, for all its familiar power, electromagnetism holds a profound secret about unity. At the unimaginably high energies that existed just after the Big Bang, the distinctions between forces begin to blur. Physicists have proven that electromagnetism and the weak nuclear force are not separate entities, but two faces of a single, more fundamental interaction, the electroweak force. At energies above about 100 gigaelectronvolts, the kind produced in our largest particle colliders, the W and Z bosons that carry the weak force lose their immense mass, behaving much more like the massless photon. In that primordial furnace, these four particles would have been indistinguishable, mediating a unified electroweak force. It was only as the universe cooled that this symmetry broke, like water freezing into ice crystals, giving rise to the distinct electromagnetic and weak forces we observe today. This successful unification is a tantalizing clue, a stepping stone toward a grander dream, a theory of everything that might one day weave all four fundamental forces into a single, elegant equation. So the light that allows you to see these words and the subtle nuclear transformations that power the sun are, in their origin, the same phenomenon. If the forces that seem so distinct in our cool, modern universe were once a unified field, what other fundamental unities are waiting to be discovered in the echoes of creation? The electromagnetic symphony gives us light, but the universe also left behind a fossilized echo of its earliest sound. Billions of years ago, before the first stars flickered on, the cosmos was a hot, dense soup of particles and light, a seething plasma where photons and matter were locked in a constant tug of war. Gravity tried to pull matter together into clumps, while the intense radiation pressure of the light pushed it apart. This created a cosmic tug of war that sent powerful sound waves or pressure waves racing outward through the primordial fluid at over half the speed of light. These were not gentle ripples, but massive tsunamis of compression and rarefaction surging through the infant universe. Then, around 380,000 years after the Big Bang, the universe cooled enough for a pivotal event: recombination. Electrons combined with protons to form neutral hydrogen atoms. Suddenly, the fog cleared. The photons, now freed from their constant collisions with matter, streamed outward in every direction, becoming the cosmic microwave background we detect today. But those sound waves did not just vanish. They froze in place at that exact moment, leaving a permanent, spherical imprint in the distribution of matter. Each wave left a shell of slightly denser material, like a ripple frozen in a pond of cosmic dust. As the universe expanded over billions of years, gravity amplified these tiny overdensities. The matter within those frozen shells collapsed to form galaxies and clusters, while the regions between them, the troughs of the ancient waves, remained more empty. The result is a vast, three-dimensional cosmic web with a hidden rhythm. Galaxies are not scattered randomly. They show a subtle preference to be separated by a specific scale, about 500 million light-years apart. This is the signature of those primordial sound waves, now stretched to a colossal size by the expansion of the universe. Astronomers call these imprints Baryon acoustic oscillations. They serve as a cosmic standard ruler etched across the heavens. By measuring this characteristic scale in the galaxy distribution at different distances, and thus different look-back times, scientists can track how the universe has stretched over cosmic history. It is like finding a ruler of known length embedded in the fabric of space itself and watching how its markings separate over time. This allows for incredibly precise measurements of the expansion rate and the properties of dark energy. The oscillations confirm the universe is flat, and they provide independent, compelling evidence for the existence of dark energy, the mysterious force accelerating the expansion. So when we map the large-scale structure of the universe, with its great walls and vast voids, we are not just seeing where galaxies live. We are reading the sheet music from the universe's first and most monumental symphony, a bass note from creation that still dictates the spacing of everything we see. If the cosmos itself can preserve a sound wave for over 13 billion years, what other primordial rhythms are waiting to be heard in the silent architecture of the void? Einstein's discarded constant has returned to haunt our understanding of the cosmos. The cosmological constant, represented by the Greek letter lambda, is the simplest and most elegant explanation for dark energy. It is not a substance flowing through space, but a property of space itself, a fixed energy density of the vacuum. Think of it as the baseline energy of nothingness, a gentle but relentless pressure embedded in the very grid of the universe, causing new space to continuously generate between galaxies. This idea neatly fits the observation of an accelerating expansion, but it presents a universe with a predetermined and rather lonely fate, the Big Freeze. As lambda relentlessly pushes galaxies apart, the cosmic horizon shrinks for any observer. Distant galaxies will redshift beyond detection, their light stretched to wavelengths so long they become invisible. Galaxy clusters will become isolated islands in an ever-darkening sea of expanding space. Star formation will cease as interstellar gas is diluted and locked away in these isolated islands. Eventually, over trillions of years, the last stars will burn out, leaving behind a cosmos of black holes, cold stellar remnants, and drifting planets, all drifting farther and farther apart in an expanding, cooling, and silent void. This is the heat death of the universe, not a dramatic collapse, but a slow, irreversible fade to black, driven by that constant, tiny repulsion. Yet many theorists are uneasy with a simple, constant lambda. The staggering mismatch between its observed value and the theoretical prediction from quantum vacuum energy is a crisis. This has led to compelling alternatives, most notably dynamical dark energy models like quintessence. Unlike a static cosmological constant, quintessence proposes a new dynamic field that permeates space. Imagine it as a kind of cosmic fluid, but one whose density and pressure can change over time. In some models, this field could eventually decay or change its character, potentially altering the universe's fate. Could the acceleration someday slow or even reverse? The data from supernova, baryon acoustic oscillations, and the cosmic microwave background currently favor a constant lambda, but the door is not closed. The true nature of dark energy remains the greatest puzzle in cosmology. Is it a simple, immutable feature of empty space, Einstein's blunder redeemed? Or is it a dynamic, evolving entity, a fifth fundamental force quietly winding down? The answer will not only tell us what the universe is made of, but how its story ultimately ends. The cosmic microwave background is a snapshot of the infant universe, but what if the first structures to form were not stars but holes? The idea of primordial black holes suggests that in the chaotic first second of existence, when the cosmos was a seething, dense plasma, tiny regions of extreme density could have collapsed directly under their own gravity. These would not be the stellar mass black holes born from dying stars, but something far more ancient and mysterious, forged from the raw energy of the Big Bang itself. They could have formed with almost any mass, from as small as a speck of dust to many times the mass of our Sun. This makes them a compelling, if speculative, candidate for the invisible dark matter that binds galaxies. A population of asteroid mass primordial black holes, drifting unseen through galactic halos, could provide all the missing gravitational pull without requiring any exotic new particles. They would be the ultimate dark matter, not a sea of tiny particles, but a swarm of ancient, invisible celestial ghosts. But their potential role extends even further. At the center of nearly every large galaxy, including our own Milky Way, sits a supermassive black hole weighing millions or even billions of suns. How did these monsters grow so big so fast? Primordial black holes could provide the answer. A rare few, born with larger masses, could have served as ready-made seeds in the early universe. As they drifted through clouds of gas and dust, their immense gravity would have fed voraciously, allowing them to balloon in size far more quickly than a black hole starting from scratch. These ancient seeds could have been the nurseries for the galactic giants we observe today. Yet, if they exist, the smallest of these primordial black holes may be meeting a dramatic end. Stephen Hawking theorized that black holes are not perfectly black. Due to quantum effects at the very edge of their event horizons, they should slowly leak radiation and lose mass. For a stellar mass black hole, this Hawking radiation process is unimaginably slow, taking far longer than the current age of the universe to evaporate. But for a tiny primordial black hole with the mass of a mountain, the story is different. Its evaporation would accelerate as it shrank, culminating in a final, violent burst of high-energy gamma rays. Some astronomers have searched the sky for these telltale flashes, which would be a signature of a tiny, dying black hole from the dawn of time. While no definitive detection has been made, the hunt continues. The possibility links the very large to the very small, suggesting that the invisible scaffolding of the cosmos and the brilliant explosions in the gamma-ray sky might both be traced back to the same primordial whispers. If the first things to exist were not beacons of light but pockets of absolute darkness, how would that rewrite the very first chapter of our cosmic story? The silent universe is filled with ghosts that are constantly changing their masks. These are neutrinos, the most elusive of all known particles. trillions of them are streaming through your body every second, coming from the sun, from distant supernova, and from the Big Bang itself, yet you feel nothing. They are called ghost particles because they barely interact with matter at all, passing through entire planets as if they were empty space. For decades, physicists believed they were massless, traveling at the speed of light. But a strange anomaly in the data revealed a deeper mystery, one that forced us to rewrite the rules of particle physics. The problem was with the solar neutrinos. We knew precisely how many electron neutrinos the sun's core should be producing based on its energy output. Yet when detectors on Earth, like the famous Homestake experiment buried in a mine, counted them, they found only about a third of the expected number. Where were the missing neutrinos? The answer was not that the sun was wrong, but that our understanding of the neutrinos themselves was incomplete. They were not disappearing, they were changing. This phenomenon is called neutrino oscillation. As an electron neutrino travels through space, it does not remain a single, fixed identity. It morphs or oscillates between three different flavors: electron, muon, and tau. It is as if a messenger left the sun speaking one language, and by the time it reached Earth, it was speaking another, invisible to detectors tuned only to the original tongue. This oscillation is only possible if neutrinos have mass, however tiny. If they were truly massless and moving at light speed, time would stand still for them from their own perspective, giving them no opportunity to change. The fact that they oscillate proves they must have a small, non-zero mass, a discovery that earned the Nobel Prize and shattered the standard model of particle physics, which had predicted they were massless. This tiny mass has colossal implications. In a supernova explosion, neutrinos are not just bystanders, they are the driving engine. When a massive star collapses, 99% of its binding energy is carried away not by light, but by a stupendous flood of neutrinos. This neutrino blast, lasting just a few seconds, contains more power than the sun will emit in its entire 10 billion-year lifetime. It is this outflow that literally pushes the outer layers of the star into space, seeding the cosmos with heavy elements. The oscillations of these neutrinos as they race through the exploding star can affect which elements are forged in that incredible fire. Furthermore, because they escape the stellar core unimpeded, neutrinos are our only direct probe into the heart of the sun. The light we see from the sun's surface was produced thousands of years ago after a slow, random walk outward. But solar neutrinos come straight from the core's fusion furnace, giving us a real-time snapshot of the processes that power our star. By catching these shape-shifting ghosts, we are reading a live diary of the solar interior. So these phantoms, with their vanishingly small mass and constant identity crisis, are both architects of stellar destruction and messengers from the center of our star. If the lightest, most elusive things we know can hold such transformative power, what other subtle, shifting forces are at work in the dark? The ghostly neutrinos change their identities, but sometimes the universe sends a signal from a machine we built ourselves. In the late 1980s, as scientists tracked the Pioneer 10 and Pioneer 11 spacecraft on their journeys out of the solar system, they noticed something deeply odd. The probes, now billions of miles from Earth, were slowing down just a tiny bit more than they should have been. This minuscule deceleration toward the sun was equivalent to a constant, gentle tug about 10 billion times weaker than the gravity we feel on Earth's surface. It was dubbed the Pioneer Anomaly. For decades, this faint whisper from the depths of space haunted physicists. Was it a sign of new physics, a flaw in our understanding of gravity itself? The most tantalizing explanation was not dark matter, but a radical rethinking of the force that shapes the cosmos. The Pioneer Anomaly seemed to echo a much larger problem, the same one that revealed dark matter in the first place, the rotation of galaxies. Stars orbit too fast at the edges of galaxies, and the Pioneer probe seemed to be experiencing a similar, unexplained extra pull. This led some scientists to propose a breathtaking alternative, What if we do not need invisible matter? What if instead our equations for gravity are simply wrong on very large scales or in regimes of extremely weak acceleration? This idea is called modified Newtonian dynamics, or MUND. Proposed by physicist Mordechai Milgrom in the 1980s, MUND suggests that Newton's law of gravity, and by extension Einstein's general relativity, needs a tweak when gravitational acceleration becomes very, very small, like it is in the outer reaches of a galaxy or in the deep space between stars. In these regimes, MUND proposes gravity falls off more slowly than the traditional inverse square law predicts. This extra gravitational oomph at low accelerations could, in theory, explain why stars on the galactic fringe orbit so quickly without requiring any invisible dark matter halo. It is a beautifully simple idea: replace an unseen substance with a modified law, and for spiral galaxies, MUND works surprisingly well, often matching their rotation curves with precision. The Pioneer anomaly, occurring in the extremely weak gravity of the outer solar system, looked for a time like it could be the first direct evidence of this modified gravity in our own cosmic backyard. The debate ignited. On one side, proponents of MUND argued for elegance and a universe free of mysterious, undetected particles. On the other, defenders of the standard dark matter model pointed out that while MUND could explain individual galaxy rotations, it struggled mightily with other evidence. The Bullet Cluster, for instance, is a spectacular collision of two galaxy clusters. Observations show that the mass, mapped via gravitational lensing, is separated from the visible galaxies, suggesting dark matter was stripped away during the collision and left behind. MUND, in its basic form, has a very hard time explaining this separation. Furthermore, the detailed structure of the cosmic microwave background, the distribution of galaxies across the universe, all fit beautifully within a dark matter model but require additional, complex tweaks under MUND. As for the Pioneer anomaly itself, the mystery found a more mundane solution. After years of painstaking analysis, a team of scientists determined that the anomalous deceleration was most likely due to an effect they had initially overlooked: the gentle, uneven push of heat. The spacecraft's radioactive power sources generated heat, and that heat, radiating off the craft's surfaces, created a tiny but constant thrust, just enough to account for the observed slowdown. It was a thermal whisper, not a gravitational revolution, so the Pioneer anomaly faded as evidence for new gravity. Yet, the debate between dark matter and modified gravity is far from over. New, more sophisticated theories of modified gravity, like tensor vector scalar gravity, continue to be developed and tested. They represent a profound philosophical fork in the road. Is the universe filled with something we cannot see, or are we simply not reading the rulebook correctly? The answer will determine whether we must discover a whole new form of matter, or rewrite one of the oldest and most fundamental laws of nature. The debate over gravity's rules points to a cosmos shaped by its earliest moments, moments that may have left behind scars. Among the most exotic relics predicted by cosmology are cosmic strings, theoretical cracks in the fabric of reality itself. Picture the universe cooling from its initial unified state, like water freezing into ice. When water freezes, the ice crystals that form often meet at imperfect boundaries, creating cracks and fissures. In a similar way, as the fundamental fields of the universe underwent dramatic phase transitions a fraction of a second after the Big Bang, they might not have settled evenly everywhere. These misalignments could have created stable, one-dimensional defects, infinitesimally thin threads of concentrated energy stretched across the cosmos. These are cosmic strings not made of matter but of pure spacetime strain. A cosmic string would be a flaw in the geometry of the universe, a rip in the canvas of reality. Though thinner than a proton, a string would possess unimaginable density, with a single inch of it potentially weighing more than a mountain range. Their gravitational influence would be bizarre and unique. Because they are under immense tension, they pull inward on themselves, creating a strange gravitational effect. Space around a straight cosmic string is not curved in the usual way, it is conical. Imagine taking a flat piece of paper and cutting out a thin pizza slice wedge, then taping the edges back together. The surface is now flat everywhere, but if you walk in a circle around the tip where the wedge was removed, you would traverse less than 360 degrees. This is the geometry around a string. Light passing on either side of it would follow this conical space, meaning an object behind a cosmic string could appear to us as two identical images, a perfect cosmic mirage. Astronomers have searched for such telltale double images of galaxies or quasars, but so far, none have been conclusively linked to a string. The true signature of a cosmic string would be its motion. Theorists suggest these relics could be vibrating, whipping through the cosmos at speeds close to light. Such violent oscillations would create ripples in spacetime, generating a steady background hum of gravitational waves distinct from the chirps of black hole mergers. Some models even suggest that the immense tension in a loop of string could cause it to pinch off, collapsing into a burst of gravitational radiation. Finding this specific signal in observatories like LIGO would be the smoking gun. While no evidence for cosmic strings yet exists, their possibility reminds us that the infant universe was a place of extreme physics where the very rules of existence were being written. If such defects formed, they would be the ultimate fossils, one-dimensional threads woven into the expanding cosmos from its very first moments, silent wires humming a song from the dawn of time. What other permanent scars might the birth of reality have left upon the void? The cosmic strings are hypothetical scars, but another threat is woven into the vacuum itself. Our universe may be living on borrowed time, resting in a state of false stability. According to our best models in particle physics, the Higgs field that gives particles mass might not be in its lowest possible energy state. Think of it like a marble resting in a small dip on the side of a much steeper hill. The dip is stable for now, but it is a false valley, a metastable state. A sufficiently powerful quantum event could, through a process called quantum tunneling, knock that marble out of its dip and send it rolling down into the true valley far below. In cosmic terms, this event would create a microscopic bubble of true vacuum, where the laws of physics are completely different. The fundamental constants we rely on, like the strength of electromagnetism or the mass of an electron, would be rewritten. This bubble would then expand in all directions at the speed of light, its wall a sphere of annihilation that transforms everything it touches. There would be no warning and no possibility of escape. One moment, the universe as we know it exists. The next, an advancing wall of new physics, a sphere of true vacuum, consumes everything, rewriting the rules of reality itself. This is vacuum decay, the ultimate existential reset button. The probability of such an event happening in any given region of space in any given year is astronomically small, perhaps less than 1 in many trillions. But given the vast size and age of the universe and the infinite future ahead, some physicists argue it becomes almost a statistical certainty over a long enough timeline. It is a silent, invisible threat born from the mathematics of the very fields that give us substance. The universe we inhabit, with its stars, planets, and life, could be nothing more than a temporary, local fluctuation in an infinite sea of a more stable but utterly alien nothingness. We are living in a cosmic soap bubble, and the pin is somewhere in the quantum foam. The threat of vacuum decay emerges from our current equations, but what if our map of reality is missing an entire continent of forces? For over a century, physics has operated with a rulebook of 4 fundamental interactions: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. This quartet seems to explain everything from the atom to the cosmos. Yet, a growing chorus of whispers from the frontiers of experiment suggests we may be on the verge of a monumental discovery, a fifth force of nature. This would not be a minor tweak, but a paradigm shift, revealing a hidden layer of interaction that has been operating in plain sight, unnoticed because its effects are so subtle or so rare. The hunt for this phantom force is driven by persistent anomalies, tiny cracks in the flawless facade of the standard model. One of the most compelling comes from the behavior of a heavier cousin of the electron, the muon. In experiments at Fermilab, researchers store muons in a perfectly calibrated magnetic ring and watch them wobble as they decay, a wobble dictated by their internal magnetism. According to every known calculation, this wobble, known as the muon's magnetic moment, should have a precise value. But the muons at Fermilab are wobbling just a little bit faster than predicted. This discrepancy, though minuscule, has stubbornly persisted across years of increasingly precise measurements. One tantalizing explanation is that the muons are being nudged by virtual particles associated with a brand new, undiscovered force. These fleeting particles popping in and out of the quantum foam could be the carriers of a fifth interaction, subtly altering the muon's dance in a way the standard model cannot account for. An even more provocative hint comes from an unexpected place, the heart of the atom. A team of physicists in Hungary studying the decay of excited beryllium nuclei observed a bizarre anomaly. When the beryllium nuclei excited, they emitted pairs of electrons and positrons that flew away at a very specific angle, suggesting they were the decay products of a new, very light particle with a mass of about 17 million electron volts. They named it the X17 particle. This potential discovery is electrifying because the properties of this X17 do not fit any known particle. It could be a force carrier, a boson for a fifth force that acts over a very short range, perhaps only a few times the width of an atomic nucleus. Some theorists propose this could be the missing link, a portal particle that mediates an interaction between the ordinary matter of our world and the shadowy realm of dark matter. Imagine if dark matter particles could talk to our world not just through gravity, but through this feeble new force. It would be a cosmic dialogue we have been deaf to until now. To test these tantalizing possibilities, physicists are designing exquisitely sensitive experiments. They are looking for forces that are weaker than the weak nuclear force but stronger than gravity, with a range so short they have escaped detection in all previous searches. Some experiments use precisely engineered, microscopic cantilevers to feel for an extra attraction between dense materials. Others search for slight twists in a suspended bar, looking for a hidden torque that could signal an interaction with a dark sector particle. The goal is to probe the forces that govern the dark universe, forces that might only reveal themselves when we push our instruments to the very edge of the quantum noise. Finding a fifth force would be more than just adding a new entry to a list. It would be the first crack in a wall, revealing a whole new landscape of physics beyond our current understanding. It could provide the crucial bridge to dark matter, explain the matter-antimatter asymmetry of the universe, or even hint at extra dimensions of space. The search is a testament to a profound truth that the most fundamental rules of our universe may still be waiting to be read. A neutron star's magnetic field can bend reality itself. Within the crushing density and unimaginable magnetism of these stellar corpses, a quantum quirk emerges that links the cosmic to the subatomic, a phenomenon called the chiral magnetic effect. To understand it, we must venture into the world of quarks and gluons, the building blocks of protons and neutrons. Under normal conditions, these particles are perpetually confined. But recreate the searing temperatures of the early universe, as we do in heavy ion colliders on Earth, or as nature does in the collision of two neutron stars, and a new state of matter emerges, a quark-gluon plasma. In this primordial soup, quarks can roam almost freely. Now, apply an immensely powerful magnetic field, like the trillion Gauss fields surrounding magnetars or generated in those violent cosmic crashes. Something extraordinary happens. The magnetic field can separate left-handed and right-handed quarks based on their spin direction relative to their motion, a property called chirality. This separation creates an imbalance, and that imbalance within the seething plasma drives an electric current that flows directly along the lines of the magnetic field itself. It is a self-sustaining dynamo born from quantum asymmetry. This effect is more than a laboratory curiosity. It is a direct probe of fundamental symmetries in the laws of physics. Specifically, it tests a symmetry known as parity, which is the idea that the laws of physics should be the same for a system and its mirror image. The chiral magnetic effect reveals that in these extreme environments, parity can be violated. The mirror image behaves differently. The current only flows one way along the magnetic field, breaking the left-right symmetry of the vacuum. This gives us a way to study symmetry-breaking conditions that were prevalent a microsecond after the Big Bang. In the cosmos, this effect could be a hidden engine within the most magnetic objects we know. The magnetospheres of magnetars, neutron stars with magnetic fields 1,000 trillion times stronger than Earth's, may be shaped by these chiral currents. The phenomenon could influence how these stars release their pent-up energy in starquakes and colossal flares, events so powerful they can affect Earth's upper atmosphere from across the galaxy. It suggests that the most intense magnetic fields in the universe do not just guide plasma, they can generate it from the quantum vacuum, twisting the rules of particle physics into a cosmic-scale battery. So, within the heart of a colliding star or the fury of a magnetar's flare, we may be witnessing a direct conversation between the force that guides compass needles and the deepest-handed rules of the quantum world. If a magnetic field can summon electric currents from the broken symmetry of empty space, what other invisible dials are being turned in the hearts of these stellar monsters? A rotating black hole does not just warp space, it twists it into a vortex. This is frame dragging, also known as the lens-thirring effect, a prediction of general relativity where a massive spinning object literally pulls the fabric of spacetime around with it. Picture a heavy, spinning ball submerged in a vat of thick honey. As the ball rotates, it does not just sit there, it drags the surrounding honey into a swirling motion. In the same way, a rotating planet or star drags the spacetime around it, forcing the very grid of reality to circulate. The effect is incredibly subtle for objects like Earth, but it is real. To measure it, scientists launched the Gravity Probe B satellite, a marvel of precision engineering. It carried 4 of the most perfect gyroscopes ever made, spheres of quartz so smooth that if they were enlarged to the size of Earth, their tallest mountain would be just a few feet high. The mission was to place these gyroscopes in a perfect polar orbit around our planet and watch. According to Newton, their spin axes should have pointed forever at a fixed guide star. But Einstein predicted 2 tiny shifts. 1, the geodetic effect from Earth's mass simply denting spacetime, and 2, the far smaller frame dragging effect from Earth's rotation tugging spacetime along with it. After years of painstaking data analysis, the team confirmed both. The axes of the gyroscopes had drifted by the exact minuscule amounts predicted. The very frame of reference around our planet is not static, it is being gently stirred by the planet's spin. Now amplify this effect from a planet to a monster. Around a rapidly spinning Kerr black hole, frame dragging is not a subtle drift, it is a cosmic maelstrom. The twisting of spacetime becomes so violent that it creates a region just outside the event horizon called the ergosphere. Here, spacetime itself is dragged around the black hole faster than the speed of light. Nothing can stand still, not even light. Matter caught in the ergosphere is whipped into a frenzied orbit, and this has profound consequences for the black hole's most brilliant features, its accretion disk and relativistic jets. The swirling spacetime acts like a giant cosmic paddle, transferring incredible rotational energy to the infalling matter. This supercharges the accretion disk, making it far hotter and brighter than around a non-spinning black hole. Furthermore, the twisted magnetic field lines anchored in this whirling space can be wound up like cosmic rubber bands, launching beams of matter and radiation, the relativistic jets, out from the poles at nearly light speed. These jets can stretch for millions of light years, shaping entire galaxies and seeding the intergalactic medium with energy. So, from the faint whisper detected by a satellite orbiting Earth to the furious vortex that powers the brightest beacons in the universe, frame dragging reveals that mass does not just tell spacetime how to curve, spin tells spacetime how to swirl. If a rotating planet can gently tug the fabric of reality, what unimaginable whirlpools are generated by the spinning hearts of quasars hidden from our view? The vortex of a spinning black hole twists space itself, but at the heart of every atom, another rule enforces a strict cosmic order. This is the Pauli exclusion principle, the quantum law that gives matter its substance and prevents the universe from collapsing into a formless, dense blur. It is not a force in the traditional sense of a push or a pull, but a fundamental prohibition, a cosmic bouncer that says no two identical fermions can occupy the exact same quantum state. Fermions are particles like electrons, protons, and neutrons, the building blocks of atoms. Their quantum state is defined by a set of properties like energy levels, spin, and orbital path. The principle declares that no two electrons in an atom can have the exact same set of these quantum numbers. This simple rule has staggering consequences. It is the reason atoms have structure and size. In an atom, electrons arrange themselves in shells around the nucleus, like seats in a theater filling from the front row back. The first shell can only hold 2 electrons, the next can hold 8, and so on. An electron cannot drop into a lower, already occupied seat. It must find an empty one farther out. This shell structure, dictated by Pauli's exclusion, is the entire foundation of chemistry. It explains the periodic table, why elements react the way they do, and why gold is different from lead. It gives matter its rigidity because when you push your hand against a table, the electrons in your atoms are repelled by the exclusion principle, preventing them from occupying the same space as the electrons in the table. It is not electromagnetic repulsion you feel first. It is this quantum rule of personal space, but the principle's most dramatic role emerges in the death of stars. When a sun-like star exhausts its nuclear fuel, its core collapses under gravity. The collapse squeezes electrons and atomic nuclei into an incredibly dense state. Eventually, the electrons are packed so tightly that the Pauli exclusion principle kicks in as the dominant resistance. No 2 electrons can be in the same state, so they are forced into higher and higher energy levels, creating an outward pressure known as electron degeneracy pressure. This pressure is not thermal like in a normal gas, it is a pure quantum mechanical effect. It halts the collapse completely, creating a white dwarf, a stellar corpse about the size of Earth but with the mass of our Sun. A teaspoon of its material would weigh tons. The white dwarf is held up not by fire but by this quantum rule against overcrowding. There is, however, a limit to this support. An Indian astrophysicist, Subramanian Chandrasekhar, calculated that if a white dwarf's mass exceeds about 1.4 times the mass of our Sun, even electron degeneracy pressure fails. Gravity overwhelms the exclusion principle, and the collapse continues into a neutron star or black hole. In that final surrender, we see the boundaries of this quantum law. From the chemistry of life to the fate of stars, the universe is structured by this invisible mandate that particles must maintain their individuality. If this rule were to suddenly vanish, all atomic structure would dissolve, and every object in the cosmos would implode into a singularity. So we exist in a universe that enforces a kind of quantum democracy, a fundamental right for particles to be different. What other silent, prohibitive laws are maintaining the delicate architecture of everything we know? Light itself can push. This is radiation pressure, the subtle but relentless force exerted by photons, the massless particles of light. Every beam of sunshine, every flash of a camera carries not just energy but momentum. When a photon strikes a surface and is absorbed or reflected, it gives that surface a tiny, imperceptible nudge. Across the vast emptiness of space, this gentle push becomes a cosmic sculptor. Look at a comet swinging around the sun. Its brilliant tail, streaming millions of miles behind it, is not simply blown by the solar wind. The comet's dust tail, broad and softly curved, is created by radiation pressure from sunlight pushing the fine grains of dust away from the comet's nucleus. The pressure of light physically sweeps the dust into that majestic arc, a visible testament to photons at work. This force shapes some of the most beautiful objects in the galaxy, planetary nebulae. When a sun-like star dies, it puffs off its outer layers in a series of gentle shells. The hot, exposed core then floods this expanding cloud with intense ultraviolet radiation. This light does not just illuminate the nebula, it rams into it. The radiation pressure pushes on the gas and dust, sculpting the cloud into intricate, glowing forms, from delicate bubbles to complex hourglass shapes. The light itself becomes the chisel, carving the final masterpiece of a star's life. But radiation pressure is not just an artist, it is also a cosmic limit. For the most massive stars, those born with dozens of times the mass of our Sun, this force defines their very existence. These stellar giants burn with such ferocious intensity that the outward pressure of their own light becomes a significant counterforce to the inward crush of gravity. As such a star ages and grows even brighter, the radiation pressure pushing from within can become so powerful that it begins to blow the star's own outer layers away in a tremendous stellar wind. This process limits how massive a star can become before it literally starts tearing itself apart with its own light. There is an upper boundary, and radiation pressure is the wall. Here on Earth, this same principle offers a pathway to the stars. The concept of a solar sail turns this subtle force into a practical engine. A solar sail is a vast, ultra-thin, reflective sheet deployed in space. Photons from the sun, reflecting off its mirrored surface, impart their momentum, giving the sail a continuous, gentle push. Unlike chemical rockets that carry and expend finite fuel, a solar sail draws propulsion from the sun itself. It can accelerate slowly but steadily for years, eventually reaching speeds that could carry a probe to the outer planets, or even to another star system, given enough time. Projects like the Planetary Society's Light Sail have already demonstrated this technology in Earth orbit, proving that we can indeed sail on sunbeams. It is a profound thought that the same gentle pressure that sculpts a comet's tail and defines the lives of giant stars could one day propel our first dedicated vessels between the stars. The universe is filled with invisible pushes and pulls, but perhaps none is more poetic than the idea that light, the very messenger that shows us the cosmos, also holds the potential to carry us into its depths. The same rule that guides a hurricane's spin also sculpts the arms of a galaxy. On a rotating planet or star, any object moving freely does not travel in a straight line from the perspective of someone spinning with it. This apparent deflection is the Coriolis effect, a force that is not a true push or pull, but a powerful illusion born from motion itself. Picture yourself on a perfectly smooth, rotating merry-go-round. If you try to roll a ball directly toward the center from your spinning viewpoint, the ball will appear to curve to one side. It is not actually being pushed, it is simply moving in a straight line while you and the platform rotate beneath it. This is the essence of the Coriolis effect. On Earth, its influence is written across our planet's fluid envelope. As air flows from high-pressure zones to low-pressure zones, the Earth's eastward rotation deflects that motion. In the northern hemisphere, the deflection is to the right, causing low-pressure systems like hurricanes to spin counterclockwise. In the southern hemisphere, the deflection is to the left, spinning systems clockwise. This is why hurricanes never cross the equator. The Coriolis effect vanishes right at that line, robbing the storm of its spinning engine. The same force shapes the great ocean currents like the Gulf Stream, bending their paths into the massive, rotating gyres that dominate our oceans and redistribute heat around the globe. Even the flight paths of long-range missiles and aircraft must account for this subtle drift, or they will miss their targets by miles, but the true scale of this effect is cosmic. Our Milky Way is a spinning disk, and the Coriolis effect operates there on a galactic scale. As gas and dust clouds orbit the galactic center, they do not move in perfect circles. Gravitational perturbations from spiral arms or passing dwarf galaxies can push a cloud slightly inward or outward. When that happens, the Coriolis effect takes over. A cloud nudged inward will be deflected forward in its orbit, while a cloud nudged outward will be deflected backward. This deflection, combined with gravity, creates a shearing motion that stretches these clouds into the long, trailing arcs we see as majestic spiral arms. The arms are not static structures made of fixed stars. They are density waves like traffic jams on a galactic freeway, and the Coriolis effect is a key part of the traffic control system that maintains their shape. It is a stunning connection, the same kinematic rule that dictates the swirl of water down your drain, though too weakly to notice, also guides the architecture of 100 billion stars. From the storm in your sky to the grand design of an island universe, rotation leaves its invisible signature on everything that moves. If a simple consequence of a spinning frame can organize systems across such impossible scales, what other universal kinematic truths are quietly directing the cosmic dance? The Coriolis effect is a trick of perspective, but another force born from rotation feels utterly real to anyone on a spinning carousel. This is the centrifugal force, the outward push you feel when something turns. Though physicists call it a fictitious force because it arises from acceleration within a rotating frame rather than a direct interaction, its effects are undeniably concrete, shaping planets and sculpting the very disks that feed black holes. On our own planet, centrifugal force is the reason Earth is not a perfect sphere. As our world spins on its axis, every bit of it wants to travel in a straight line, but gravity pulls it into a curved path. This creates an outward push, strongest at the equator where the rotational speed is greatest. Over eons, this relentless push has battled gravity, causing the planet to bulge at its middle. Earth's equatorial diameter is about 27 miles wider than its polar diameter, a subtle but permanent testament to this rotational struggle. We see this force magnified in the majestic ring systems of the gas giants. Saturn's brilliant rings are not solid sheets, but trillions of individual ice particles, each one in its own orbit around the planet. For any given particle, two forces are perfectly balanced. Gravity pulls it inward toward Saturn's immense mass. The centrifugal force generated by its orbital motion pushes it outward. Where these forces exactly cancel, the particle achieves a stable circular orbit. This balance is the very definition of orbital motion, a perpetual fall toward the planet matched by an outward flight, resulting in a graceful, endless curve around the world. This principle scales up to the most violent environments in the cosmos. Around a black hole or a newborn star, swirling clouds of gas form an accretion disk. As material spirals inward, drawn by immense gravity, it also orbits at tremendous speed. This rotation generates a powerful centrifugal force that fights the inward pull, preventing the gas from plunging directly into the abyss. Instead, the material is forced to gradually lose energy through friction and magnetic turbulence, slowly drifting inward in a tight, hot spiral. The balance between the inward crush of gravity and the outward push of rotation is what creates the flat, pancake-like structure of these disks. It is this equilibrium that allows the disk to shine with blistering radiation, powering quasars and lighting up stellar nurseries. Without centrifugal force, there would be no orbits, only catastrophic collisions and swift, direct plunges into gravity's maw. It is the silent partner to gravity, the push that makes the cosmic dance possible, from the ice grains of Saturn's rings to the superheated plasma whirling at the edge of oblivion. The centrifugal force defines orbits, but at the quantum scale, a particle cares little for barriers. In the subatomic realm, a proton approaching another proton does not see an impenetrable wall of electromagnetic repulsion, it sees a hill. And according to the bizarre rules of quantum mechanics, there is a chance, however small, that it can simply appear on the other side. This is quantum tunneling, the probabilistic magic trick that allows particles to pass through energy barriers they classically should not be able to overcome. It is not a violation of physics, but a consequence of the wave-like nature of all matter. A particle's location is described by a probability wave, a cloud of potential. Where that wave meets a barrier, it does not abruptly drop to zero. It decays exponentially, like a whisper fading down a long hallway. There remains a finite, non-zero probability that the particle will be found on the far side of the barrier, as if it had tunneled through. This is not a theory, it is a daily reality. It is the reason our sun shines. In the solar core, protons must collide with enough energy to overcome their fierce mutual repulsion and allow the strong nuclear force to fuse them. The temperatures, while immense, are still theoretically too low to give every proton the classical energy needed to surmount that electromagnetic hill. Quantum tunneling provides the shortcut. A tiny fraction of protons, thanks to the spread of their probability waves, simply tunnel through the repulsive barrier, enabling the fusion reactions that power our star and every star like it. Without this quantum loophole, the universe would be dark. Tunneling is also the heartbeat of radioactive decay. In a heavy nucleus like uranium, an alpha particle, 2 protons and 2 neutrons, can be thought of as trapped in a well by the strong nuclear force. Yet, its probability wave extends beyond the nuclear walls. There is a small chance, governed by half-life, that the alpha particle will tunnel out of that well and escape, a spontaneous act of quantum leakage that transforms one element into another. This process heats the Earth's interior and provides the energy for deep space probes, but we have also harnessed this ghostly ability. The scanning tunneling microscope does not use light to see, it uses tunneling current. A needle with a tip just 1 atom wide is brought incredibly close to a surface. A voltage is applied and electrons tunnel through the empty space between the tip and the sample. By scanning the tip and measuring the minute changes in this tunneling current, scientists can map the surface atom by atom, rendering the invisible architecture of matter visible. It is a direct manipulation of quantum uncertainty to map our world. So from the heart of a star to the decay of a rock to the mapping of a molecule, quantum tunneling connects the smallest rules to the largest processes. It whispers that on the fundamental level, barriers are merely suggestions, and the universe operates on a calculus of probability, not certainty. If particles can ignore the walls we perceive, what other fundamental constraints in our reality are merely illusions waiting to be tunneled through? Quantum tunneling allows for impossible leaps, but the very rules that permit it seem impossibly perfect. The strength of gravity, the mass of an electron, the energy binding atomic nuclei, these fundamental constants are not predicted by any theory. They are numbers we must measure and plug into our equations, and if any of them were even slightly different, the universe as we know it would not exist. This eerie fine-tuning is the heart of the anthropic principle, a concept that bridges physics and philosophy. It begins with a simple, undeniable observation. The universe we inhabit is curiously suited for the emergence of complex life. Consider the force that binds atomic nuclei, the strong nuclear force. If it were just a few % stronger, protons would bind so readily that all the hydrogen in the early universe would have fused into heavier elements. There would be no stable hydrogen, no water, and no long-lived stars like our Sun. If it were slightly weaker, protons could not bind at all, and no elements beyond hydrogen would form. No carbon, no oxygen, no building blocks for life. The cosmological constant, that mysterious dark energy, is equally precarious. If it were larger by a minuscule factor, the universe would have expanded so rapidly after the Big Bang that galaxies and stars could never have coalesced. If it were negative, the cosmos would have collapsed back on itself long before life had a chance to arise. The list goes on, from the precise balance of forces that allows for stable atoms to the specific energy levels in the carbon atom that enable its abundant production in stars. The universe seems set to a very specific, life-permitting recipe. So what does this mean? The anthropic principle offers two starkly different interpretations. The first is a selection effect, a simple statement of observational bias. We should not be surprised to find ourselves in a universe capable of producing us. We are, by definition, observers who can only exist in a universe with the right conditions. It is like a puddle marveling at how perfectly the hole it fills matches its shape. The puddle does not realize the hole came first, it simply conforms. In this view, there is no deeper reason, no designer. We are here because this universe allows it, and we are asking the question. The second interpretation is far more expansive and suggests a staggering reality beyond our cosmic horizon. If the fundamental constants are not necessary but contingent, perhaps they are different in other realms of existence. This leads to the idea of a multiverse, a vast or perhaps infinite ensemble of universes, each with its own random set of physical laws and constants. In most of these universes, the numbers are wrong. They collapse instantly or form only empty space or produce no complex structures. But in a vanishingly small fraction, by pure chance, the numbers line up just right. We inevitably find ourselves in one of those rare, life-friendly universes, not because ours is special, but because we could not arise anywhere else. The multiverse transforms fine-tuning from a mystery into a statistical inevitability. This idea gains some credence from theories like eternal inflation, where different regions of an ever-expanding cosmos could undergo different symmetry-breaking events, crystallizing into distinct universes with different laws. While we cannot observe these other universes directly, the anthropic principle becomes a powerful tool within such a framework, explaining why we measure the constants we do. It is a humbling and dizzying thought. The precise laws we work so hard to decipher may be nothing more than local bylaws in our particular cosmic neighborhood, with an infinity of other rulebooks written in the darkness beyond. Whether a simple logical tautology or a window into a reality of unimaginable plurality, the anthropic principle forces us to confront a profound question. Does the universe care that we are here, or are we just incredibly lucky to be asking? Perfect symmetry is a beautiful idea, but it makes for a rather boring universe. In the first moments after the Big Bang, the cosmos was a place of ultimate unity and perfect balance, a hot, featureless soup where the fundamental forces were one and particles were massless. If that perfect symmetry had persisted, nothing would ever have changed, nothing would ever have clumped together, and we would not be here to talk about it. The universe gained its rich structure, its forces, and its very substance through a series of cosmic accidents called symmetry breaking. Think of it like a perfectly round, smooth ball balanced on the very tip of a hill. The ball is symmetrical, every direction from the top is identical, but it is also unstable. The slightest nudge, the tiniest fluctuation, will send it rolling down into a specific valley below. The perfect symmetry of the hilltop is broken, and the ball now rests in a particular, chosen direction. That nudge was the cooling of the universe. As the cosmos expanded and its temperature dropped, the unified fields that governed reality could no longer maintain their high-energy, symmetrical state. They had to settle into a lower energy configuration, and in doing so, they made a choice. A classic, tangible example is a magnet heating up. Take a simple iron bar magnet. When it is cold, it has a distinct north and south pole, a clear direction, a broken symmetry. but heat that magnet to a critical temperature and something fascinating happens. The intense thermal energy jostles the atomic dipoles so violently that they can no longer align. The magnet loses its polarity entirely. It becomes perfectly symmetrical with no preferred magnetic direction. Now let it cool. As the temperature drops, the dipoles will suddenly snap into alignment again. But which direction will they choose? North, south, east, west? The laws of physics governing the cooling are perfectly symmetrical. They do not favor one direction over another. Yet, a direction is chosen spontaneously based on a random fluctuation. The symmetry of the hot state is broken and a specific order emerges from the chaos. This is precisely what happened in the early universe, but on a scale and with consequences we are still unraveling. The first and most dramatic breaking was likely the separation of gravity from the other forces. Then, as the universe cooled further, the grand unified force that combined the strong and electroweak forces broke apart. A fraction of a second later, the electroweak force itself shattered into the distinct electromagnetic and weak nuclear forces we recognize today. Each break introduced new properties into the cosmos. The most famous example of this is the Higgs field. In the hot, early universe, the Higgs field had a value of 0 everywhere, perfectly symmetrical. But as the temperature fell below a critical threshold, this field, like our cooling magnet, had to choose a new, non-zero value. It settled into its lowest energy state everywhere at once, a process called the Higgs mechanism. This spontaneous breaking of the electroweak symmetry is what gave the W and Z bosons their immense mass while leaving the photon massless. It is why the weak force is so short-ranged and electromagnetism is infinite in reach. More broadly, it gave mass to all the fundamental particles that interact with the field. The universe went from a state of symmetric, massless freedom to one of broken symmetry, where particles had weight and forces had character. This pattern of breaking did not happen just once. It likely happened in stages, each transition potentially releasing immense energy and possibly creating cosmic defects like those hypothetical strings. The asymmetries we see today, from the fact that matter dominates over antimatter to the very existence of left-handed and right-handed particles, are all frozen relics of those ancient choices. Our reality is not built on perfect, eternal laws, but on a sequence of historical accidents frozen into the fabric of the cosmos as it cooled. We are the products of a universe that chose a path, breaking its own perfect symmetry to become the complex, structured, and life-friendly place we call home. What other hidden choices made in that first second of time are still echoing through the galaxies? Symmetry breaking gave the universe its rules, but who is reading them? We arrive at the final, most contentious unseen force, one that does not operate in the vacuum of space or the heart of an atom, but within the realm of awareness itself. This is the observer effect in quantum mechanics, and it suggests that consciousness may be inextricably woven into the fabric of reality. The problem begins with a simple, baffling fact. In the quantum world, a particle like an electron does not have a definite position or momentum until we measure it. Instead, it exists in a superposition, a spread-out cloud of probability described by its wave function. This wave function encodes all the possible states the particle could be in. The act of measurement, however, does something drastic. It forces the particle to pick one definite state from the many possibilities. The wave function is said to collapse, but what exactly constitutes a measurement? Is it the physical interaction with a detector, or does it require a conscious mind to register the result? The most famous interpretation, the Copenhagen interpretation championed by Niels Bohr and Werner Heisenberg, takes a starkly pragmatic view. It says we should not ask what a particle is doing when we are not looking. The mathematics only describes the outcomes of measurements. In this view, the collapse is a fundamental, irreducible process triggered by the interaction between the quantum system and a classical measuring device. Yet the line between quantum and classical is notoriously fuzzy. Where does it end? Some physicists like John von Neumann and Eugene Wigner pushed the logic further. If a measuring device is just a collection of atoms that themselves obey quantum laws, then why does it cause collapse? They propose that it is not the device, but the conscious perception of the information that finally resolves the superposition. In this radical view, consciousness is the ultimate catalyst that translates possibility into actuality. Imagine the classic thought experiment, Schrödinger's cat. The cat in the box is in a superposition of being both alive and dead, linked to the random decay of a radioactive atom until someone opens the box and looks. According to the most extreme interpretation, it is not the opening of the box that matters, but the conscious observation of the cat's state that forces the universe to decide. This idea is profoundly unsettling. It seems to place human consciousness or any consciousness at the center of physical law, suggesting the moon is not there when no one looks. Unsurprisingly, this has sparked fierce debate and alternative interpretations. The many worlds interpretation, for instance, offers a dizzying escape. It proposes that the wave function never collapses. Instead, at the moment of measurement, the universe splits into multiple branches. In one branch, you see a live cat. In another, equally real branch, a different version of you sees a dead cat. Every possible outcome occurs in some branching timeline, and consciousness simply experiences one thread of this vast, ever-diverging multiverse. Here, observation does not collapse anything, it just selects a path. Other interpretations, like objective collapse theories or pilot wave theory, seek to remove the observer entirely by adding new physics or hidden variables. Yet the core mystery persists in laboratory experiments. In the double-slit experiment, a single electron fired at a barrier with two slits behaves like a wave, passing through both and creating an interference pattern. But if you place a detector to see which slit it goes through, the electron behaves like a particle, the interference vanishes. The very act of obtaining which path information changes the outcome. It is as if the electron knows it is being watched. This is not a quirk of electrons. It has been demonstrated with larger and larger molecules, pushing the boundary of where quantum weirdness applies. So where does this leave us? The idea that consciousness causes collapse remains a minority view among physicists, seen by many as placing the cart before the horse. Yet it raises a haunting philosophical possibility. For centuries, we have viewed the universe as a grand machine operating independently of mind. Quantum mechanics hints that the separation between observer and observed may be an illusion. The act of questioning, of measuring, of being aware, might be a participatory force in shaping the reality we perceive. It suggests that the final unseen force shaping the universe is not out there in the dark between galaxies, but within the luminous darkness of our own perception, asking the questions that bring the answers into being. From the silent pressure of light to the ghostly whispers of neutrinos, we have journeyed through a cosmos governed by the unseen. 30 hidden architects, from the titans to the subtle, collectively author every event in the universe's grand narrative. Dark energy stretches the stage itself, while dark matter provides the invisible scaffold. The quantum foam seethes with potential, and the Higgs field grants substance to the void. Entanglement weaves instantaneous connections across the void, and gravitational waves carry the news of catastrophic mergers. Each force, each field, each rule is a thread in an unimaginably complex tapestry, one where the push of a photon and the prohibition of a quantum rule are equally vital. This is not a universe of isolated phenomena, but a single, interconnected story written by actors we are only beginning to perceive. The night sky is not a static painting, but a dynamic performance, and every star, every galaxy, is a marionette moved by these countless invisible strings. So the next time you look up, remember you are not just seeing points of light. You are witnessing the final, luminous effect of a hidden symphony. Which of these unseen forces captures your imagination the most? Is it the dark energy that will decide our cosmic fate, or the quantum entanglement that suggests distance is an illusion? Share your thoughts below and keep wondering about the magnificent, invisible machinery at work just beyond the edge of sight. The search for a single equation that explains it all is the ultimate quest of physics. We have 4 fundamental forces, each with its own rulebook, but in the first, unimaginable flash of the Big Bang, they were not separate, they were one. A unified force, the dream of a theory of everything, is to rediscover that primordial unity, to write a single, elegant framework from which gravity, electromagnetism, and the nuclear forces naturally emerge as different facets of a deeper truth. This is not just about tidying up the laws of physics, it is about reading the universe's original source code. 2 towering but very different paths dominate this search. The first is string theory. It proposes a breathtaking shift in perspective. The fundamental ingredients of reality are not point-like particles, but incredibly tiny, vibrating loops of energy, strings. Just as different vibrations of a violin string create different musical notes, the different resonant patterns of these fundamental strings give rise to all the particles we see, from quarks to photons. In this view, an electron is not a dot, it is a specific note played on a cosmic string. Gravity emerges naturally from this vibrational symphony, with the graviton, the hypothetical particle of gravity, being just another note in the repertoire. But to make the mathematics work, string theory requires something startling: extra dimensions of space. Not just the 3 we experience, but 6 or 7 more, curled up into shapes so tiny at the Planck scale that we never perceive them directly. The specific geometry of these hidden dimensions would determine the properties of our universe, like the masses of particles and the strength of forces. The other major contender is loop quantum gravity. It takes a radically different approach. Instead of adding extra dimensions, it focuses on quantizing the very fabric of spacetime itself. Imagine spacetime not as a smooth, continuous sheet, but as a woven network of finite, tiny loops. Picture a cosmic mesh, a fabric of interlinked threads of space. This network evolves in discrete steps, not continuously. In this theory, gravity is not a force in the traditional sense, but a consequence of the geometry of this spin network and its quantum dynamics. It is a theory built from the ground up to be compatible with quantum mechanics, offering a possible window into the nature of spacetime inside a black hole or at the very beginning of the universe. Both theories aim for the same goal, unification, but they approach it from opposite ends of the problem. String theory starts with particles and tries to include gravity. Loop quantum gravity starts with gravity and tries to build particles. To witness the unity they seek, we would need to rewind the cosmos to its very first moments, to the Planck epoch, a time so early that the universe was smaller than a single atom and hotter than anything we can conceive. At those insane energy scales, a trillion times greater than what our largest colliders can produce, the distinctions between forces would have melted away. Gravity would have been as strong as the other forces, and a single, unified interaction would have governed everything. We cannot build a machine that powerful, so we must search for indirect clues, for subtle fingerprints left in the cosmic microwave background, or for unique predictions about the behavior of spacetime that future gravitational wave observatories might detect. The journey toward a theory of everything is a reminder that our understanding is still in its infancy. The cosmos we see is the cooled, fractured remnant of a state of perfect symmetry. Finding the equation that describes that original unity would be the culmination of centuries of scientific discovery, a final glimpse into the mind of the universe. Until then, the search itself is the story, a testament to our endless curiosity about the hidden architecture of reality.